Thank you very much. Thank you to the organizers of bringing us together at this very beautiful place, and also this interesting across the aisle, so to speak, composition of the audience. So I'm coming from the superconducting side, and actually I would like to address one basic question, namely how can we actually marry or introduce spin-orbit interaction into superconductivity. And say the main observable that I will be advertising is a bit unusual for superconductivity. It is a nonlinear inductance, and I will explain how it comes about. So I'm from the beautiful city of Regensburg, and the work has been done by a series of talented PhD students. Simon actually is here in the audience. And Nicola Paradiso is a senior researcher in my group. The materials are coming from the group of Mike Manfra from Purdue University, and these materials were a game changer. So we did actually superconductors on indium arsenide before, but it was a pain, and now we have this very beautiful epitaxial materials which are grown at Purdue. And for the interpretation of the data, we relied very much on our theory colleagues in Regensburg. So as this is a long talk with should also be a kind of tutorial, let me start very, very basic. Namely asking what is actually driving a supercurrent? Because we know usual dissipative currents, they are mainly driven by electric potential differences, which are zero in a superconductor. So there must be something else that drives a supercurrent. And the answer to this question has been given by Ginzburg and Landau. So some of you may recognize this as the second Ginzburg-Landau equation, which tells us that there is another gradient which drives a supercurrent, and this is the gradient of the phase of the complex order parameter, and which is here what we also call the macroscopic wave function, psi. And of course, gradient of a phase is not gauge invariant. You have to properly combine it with the magnetic vector potential. So what we need in addition is actually something that brings time into the game, and that is the second Josephson relation, which relates the time derivative of a phase difference or a phase gradient, depending on whether you talk about a continuous superconductor or something like a weak link. So here this is the local version of Ohm's law. But you, of course, have also the global version where voltage is resistance times current. And the very same thing appears here. So voltage is a potential difference between two places in space. And similarly, you can also have a phase difference between two places in space, for instance, the two banks of a Josephson junction. So important is that the time derivative here is now related to the electrostatic potential difference. So how can we see that this equation now really has to do something with superconductivity? Well, we can take the curl of this relation. Then the phase here is actually eliminated, and we have the curl of the vector potential, which is our magnetic field, and that is known as the second London equation. And this is usually covered in, say, solid-state physics courses. And there is a prefactor here, which runs under many names. So the first name was the London parameter, superfluid density. It contains the magnetic penetration depth, lambda here. And yesterday we learned it's also called superfluid weight or superfluid stiffness. It's all the same parameter. And it describes the Meissner effect. The second thing we can do is to take the time derivative, and this time derivative of the phase here produces our electrostatic potential, And here the gradient of this electric static potential is the electric field together with the time derivative here of the vector potential. So taking this time derivative produces the second London equation, which relates the time derivative of the current with the electric field and with the very same parameter. Now, to get access to the superfluid density, the superfluid stiffness, or whatever, usually people measured penetration depth, right? However, this is difficult if you have ultra-thin films with thicknesses much smaller than the penetration depth, because there is not too much penetration. And what I learned very late is that we can get access to this quantity via this first London equation, because this is nothing but an inductance. It is a Faraday law, basically, and the prefactor here, the inverse London parameter, plays the role of what is called kinetic inductance. So this kinetic inductance comes on top of the more familiar, let me see whether I can find this point here, more familiar geometric inductance. And for a simple strip geometry, both actually are very well known. And what you see is that the second term, this kinetic inductance, becomes important in thin films, which are much thinner than a penetration depth. So precisely in the situation where it is difficult to measure the penetration depth. And yeah, so that means, in fact, this relation here tells us we should not look at the real part of the resistance, but at its imaginary part, which is inductance. To characterize superconductor, and the characteristic then is indeed the superfluid density, if you wish. Okay, so this motivates why I'm interested in inductance as a quantity to observe. Now, let me give you some examples where this actually has been used. In fact, in materials which are very similar to ours. So I will talk about it, but this is aluminum films on indium arsenide, where the intimate epitaxial interface between the two infects, so to speak, the superconductor with spin-orbit interaction, while the superconductor infects the indium arsenide with superconductivity. And what was found here in this paper by the group of Andrew Higginbotham was that the inductance develops some interesting directional dependence, which can be traced back to a spin-orbit interaction. Another example is something that I will address also in this talk, is that you can actually produce Josephson junctions with an additional phase shift. Usually, the supercurrent through a Josephson junction is proportional to the sign of the phase difference. So it is zero at zero phase difference. But in particular junctions, you can have these anomalous shifts that I will be going to discuss. Yet another important manifestation of spin-orbit interaction comes in different materials. Transition metal decalcogenide. So this is here niobium diselenide, in fact, where actually it was found that the upper critical magnetic field is far beyond what is called the Pauli limit, namely the field that is where the energy from polarizing your Cooper pairs into a paramagnetic state exceeds the energy gain from Cooper pairing. So this Pauli limit, you see, is actually here, and the critical magnetic field can exceed this by a factor of 4, 5, up to 10, actually. And that is because this valley spin-orbit interaction that you have in these materials protects the Cooper pairs against the Zeeman field. So these are called Ising superconductors. And last not least, their spin-orbit interaction can also lead, at least in theory, to phase-controlled topological transitions. And yes, so this is something that has received a lot of extension in the last 10 years. So after this, let me approach more the topic what is non-reciprocal transport? So what we call non-reciprocal is the fact that actually we can have a current where the magnitude depends on the sign of the bias. So if we have here such a semiconductor diode as the archetype, yeah, you know that there are p-n junctions. And for forward bias, you get a bigger current than for reverse bias, where the diode largely blocks the current. So you see that here you need a kind of symmetry breaking, which is on the macroscopic scale, because you have your p and your n side of the junction, or you can do the same thing, say, with Schottky diodes, where you have semiconductor on one side and metal on the other. The question is whether this can happen also for a symmetry breaking on the atomic scale, on the scale of the unit cell. And there is a very beautiful example by the group of Peter Wieder, which took bismuth crystals. So this is just a wire made from bismuth. And they introduced symmetry breaking by just torsion of this wire, right? So this is just here a twist that they have introduced. And depending on whether the twist is clockwise or counterclockwise, they found that there is a small additional contribution to the resistance, which depends linear on the magnetic field, and the sign depends on the orientation of the twist. So this is already, say, a nonlinear correction to the resistance. A few years later, they found that this can also happen in field effect transistors, so-called JFETs, where they found again here that there is a current-dependent contribution where the sign depends on the sign of the magnetic field. Say the explanation at that time was given in terms of Rashba spin-orbit interaction. So there is a competition between Zeeman fields and here the Rashba Hamiltonian, where you can actually identify the sigma here, the spin with the magnetic field, and the k here with the current. And that produces this bilinear combination of current and field in this additional contribution to the resistance. So phenomenologically, what they found out is that there is a contribution to the resistance that depends here on this cross product of magnetic field and current density. However, these were very small effects. If you look at the scales here, these are 10 to the minus 4 effects. Now, what mainly our colleagues in Japan in the last 10 years have found is that if you take the resistance in, say, the transition regime, in the fluctuation regime of superconductors, then you can boost these effects by a factor of 100, so to the 10 to the minus 2% range already. And what I am going to address in this talk is if you go fully into the superconducting regime, you can get order 1 effects, much bigger. And so an experiment that has attracted a lot of attention in the last years was coming from the group of Teruo Ono, where they introduced such stack of 3 different superconductors. So, and you see the unit cell of this stack breaks inversion symmetry. If, in addition, they apply a magnetic field here perpendicular to this Hall bar through which they send their current, they found that the critical current depended on the orientation of this bias. So you see here in green are magnetic fields which are alternating in sign. And red and blue here are 2 different bias polarities. So for one orientation of the field, the negative bias was resistive, while the positive bias was superconducting. And for the opposite field orientation, this preferred bias direction switched. So this occurs if you have, say, a positive and a negative critical current which are different, and where you bias with a current exactly between these 2. That is what they did here in this picture. When actually this paper came out, we actually measured our device, which is here the chain of Josephson junction, and found a very similar phenomenology, although for the very different reasons. Okay, so the goal to look for such non-reciprocal supercurrents actually, I think, has been reached, and there has been a huge wave of papers addressing the so-called supercurrent diode effect, which just means the effect that for at least a certain current, for positive bias, the device can be resistive, and for the opposite bias, it can be superconducting. And so I apologize for somebody who may not find his name here, but I can actually highlight Sebastian, who worked here on this problem in the context of diffusive junctions. I can highlight Davala, who with her I had a pleasure to work with last year in Regensburg, and well, many other people. So, but when this wave came up, then there were some older guys who said, this is all known, right? It is in the textbook of Barone, which you find here. It's a very beautiful book about the physics and applications of the Josephson effect. And they said, well, if you make a squid, which is asymmetric with two different critical currents here, then you can have already this observation that here the negative critical current is different from the positive one, with very similar symmetries if you invert the fields. In that sense, supercurrent diodes are not really new. So my approach to this topic is, if you wish, this is the counterpart of the semiconductor diode, where symmetry breaking occurs on the macroscopic scale because of these two unequal junctions. And the question is this possible also on the atomic scale? And the answer is yes, if you include spin-orbit interaction. So let me highlight some more examples. So the next speaker, which is Yazhen Hu, he actually found that you can have this sort of rectification or supercurrent diodes even in plain strips, metal strips. He actually, in fact, said you can replace your external magnetic field. You can replace by putting here europium sulfide, which is a ferromagnetic insulator, on top, so that you don't need these external fields and still can get your rectification. But as you see, this type of effects is also not so new. In fact, it really comes again from a macroscopic asymmetry, namely the two sides of the superconducting strip are not necessarily equal. In particular, the barrier for vortex entry can be unequal, and that is what produces the diode effect here in this case. Then there is another example from the group of Stuart Parkin, who studied exotic Josephson junctions here in terms of this, where the weak link is this semi-metal, nickel telluride, where they found, again, such a big discrepancy between critical currents. Here you can see it makes a factor 2 already. They also found if they change the in-plane magnetic field, which breaks here your time reversal symmetry, then you can find oscillation of the sign of that. And they also have a model which describes this type of effects. But with this, let me come now to our experiment and our device. So what we investigate is here, let me find again my pointer. A chain of Josephson junctions, so this is in this cartoon here, where actually we have an epitaxially grown aluminum film on top of a semiconductor quantum well here in yellow, which is indium arsenide with some shallow barriers left and back. And the transparency of this barrier here is made such that there is a good proximity effect of aluminum to the indium arsenide, meaning there is an induced gap, delta star, which is living inside the indium arsenide. And then there is an area of the indium arsenide between the aluminum banks. So this is not to scale. The gap here is, say, 100 nanometers, while this distance is only 10 nanometers, the vertical distance. And these are our Josephson junctions. Now we work deeply in the superconductive regime where the resistance is 0. And the question we ask, is there an analog of this resistive equation here? See, this is the phenomenological equation that they found in the normal state. Is there an inductive analog for this in the Josephson inductance? And so where does the Josephson inductance come from? So this is a consequence here of the two Josephson equation. You have a supercurrent that depends on phase. This, of course, has to be a 2 pi periodic function. In the simplest case, this is a sine, as you know from tunneling junctions. And there is the second Josephson relation, which connects time derivative of the phase difference. And if you take these two equations together, you see that you have a voltage that is proportional to the time derivative of a current, just in the London equations. But now the corresponding inductance is given here by the inverse of this function f prime, which is the derivative of f with respect to phi. So what we measure is the derivative of the current phase relation. This function f of phi is called the current phase relation because it connects supercurrent and phase difference in Josephson junctions. So how does this work in practice? Well, if you have here a superconducting normal metal sandwiched between two superconductors, and you are an electron that lives here in the normal conductor, as Wolfgang told you already yesterday, say if you are at energies below the energy gap, you cannot enter the superconductor unless you grab a partner from below the Fermi energy here to form a Cooper pair on the right-hand side, and then have a hole tracing back to the left side. And when the hole arrives here, it eats one partner of a Cooper pair, and the remaining sole partner has now to complete the cycle. And if you have enough electronic phase coherence, if this distance between S and S is not too long, then you can establish, say, a state, which is called an Andreev bound state, whose energy depends on the phase difference. And thermodynamics tells us that the supercurrent carried by these states is just given by the derivative of energy with respect to phase, and that it depends on the transparency of this junction. See, in mesoscopic physics, you have, say, a constriction, which has a certain probability for electrons to be transmitted. And this very same probability determines now how the spectrum of Andreev bound states look like. If the transparency is small, there is only a weak modulation here with a, say, sinusoidal variation. And if this probability for electrons to be transmitted becomes large, you see it becomes anharmonic. It has higher Fourier components and has then such a shark fin shape of current phase relation. And that is what is relevant for our junctions because they will turn out to be highly transmissive. So what we now do is, in order to gather enough inductance, we take a long chain of these junctions here so that the inductance of each individual junctions adds up. We work at relatively low frequency so that we avoid that we get excitations here of this chain. And then we find here such nice resonance curves from which we know this capacitance here, from which we can extract the inductance. And this method is actually has been developed a long time ago, but then was kind of forgotten. That will turn out to provide ample information about these junctions. In particular, say, the transparency and the induced gap. So how does it work? Let me repeat again, say, our relation here for the inductance. This is this inverse derivative of the current phase relation. So if you wish, this is the phase-current relation. So we take, let me find my pointer here again. Yeah. If we take our current phase relation like this, we actually have to take the inverse to get the phase-current relation, and then our inductance measures this slope here around zero current. And that produces a nonlinear, a current-dependent inductance, depending on how close you are to the critical current. And so these different colored dots here correspond to different bias voltages, where you see if we get very close here to this 1 microamp, let me find here, this point is already very flat, but still we can actually extract an inductance. It's a kind of lousy resonator with a quality factor around 30, so all the microwave guys are laughing. But nevertheless, this quality factor of 30 allows us to extract the inductance with 3 digits of accuracy, which is not too bad. So, and if I now plot here the inverse of the inductance, L0 over L, in a dimensionless form, and here L times current as a divided by the flux quantum, then actually say this current dependence inductance develops a kind of universal shape that depends only on the transparency. Because in this ratio we have divided out this prefactor here, I0, and it is known how this thing should actually look like. We find here a black line that corresponds to perfect conductance. Then there is a dash dotted line which corresponds to tunneling junctions with very low conductance. And you see our data, they are close to the solid line, and we can assign that there are transparencies above 90%. So this is a very highly transmissive junction. And the reason why it is so transmissive is that we go from indium arsenide underneath the aluminum to indium arsenide without aluminum within the same single crystal. So that's why there is very little reflection. And so in the limit of zero temperature, this depends here on this transparency, tau only. And because this transparency is so high, we can actually say that the dispersion of transparencies that we have between our 2000 junctions in a row and the many channels in these junctions, that we can actually interchange these averages. So, and having now the transparency, we can go now on as a function of temperature. And from the absolute value of the inductance, we can determine the number of channels, this prefactor I0 basically. And from the onset of the temperature dependence, we can determine the induced gap. And these are the parameters that completely describe the junction in a quantitative fashion. Okay, having now understood these junctions, we can ask, where is now spin-orbit interaction? And the answer is, if there is no external magnetic field, then there is a spin texture where the spins actually point perpendicular to the k vector in case of pure Rashba interaction, and they are all just happy. But if you now put in addition an in-plane magnetic field, then the spins become tilted out of the preferred direction from the spin-orbit interaction. We get a competition, and we move this, the electronic states here up and down our modified free electron parabolas. So if we draw, actually, say, the two parabolas for the two spin directions, we see that at absence of a Zeeman field, we can do Cooper pairing here with opposite k-states. But introducing now a Zeeman field actually shifts the parabolas vertically with respect to each other. And that actually now produces a different velocity for forward and backward traveling electrons. And this shift of energies and velocities, that actually provides the non-reciprocity. It needs this external field in addition to the inversion symmetry breaking by the spin orbit. So now we really modify our Andreev bound states so that they depend, they can discriminate between forward and backward transmission. Now, what actually happens if we add the spin-orbit interaction and an external field? In the simplest case, this is that we actually get a cosine contribution to the current phase relation. And if we start at low transparency, we have a simple sine, plus a cosine produces a shifted sine. So this way, this phi naught shift is generated. But the positive and the negative critical current, they are still equal. There is no diode. It's only a shift of the current phase relation, which already is non-reciprocal. But if we want the diode, we actually have to have a junction where you have higher harmonics in your current phase relation. And it is, in the simplest case, the interference between this sine 2 phi term and the cosine phi term, which now produces a peculiar distortion here. So black is in absence of the cosine phi term. It is our skewed sign. And now if we add the cosine phi term, then you see that the superposition of the terms produces a large critical current here for red and a smaller critical current there. It's simply by adding these terms. And if the magnetic field is reversed, then also the magnitude of the two critical currents is reversed. So that describes the diode behavior, so that here the maximum critical current is different, of the positive critical current is different from the negative critical current. That is the phenomenology that has been observed in many experiments. But in addition, we are not bound to the critical behavior here. Actually, if you take the derivative of the inverse of this curve, then we get a current-dependent inductance. And you see, while for zero field, we expect that this is symmetric around the current direction. For a finite in-plane magnetic field, we expect that the two parabolas are shifted against each other. That is because, say, this minimum here corresponds to the inflection point here of the current phase relation that goes away from zero. Okay? And so that is the signature in the inductance. And the advantage is that we can actually work here at very small phase bias, close to zero here, and avoid all the complications that are connected to the critical current, where you can have premature switching and many other competing effects. Okay. Somehow the guy doesn't want me to continue. So, okay. And this is exactly what we observe in experiment. This is now, we have here our chain of Josephson junctions here. And now we apply an in-plane magnetic field in different directions. So the upper graph is for parallel magnetic field, parallel or anti-parallel to the current. And you see there is no effect. It is symmetric around zero current. But if we now rotate the field so that there is a component perpendicular to the current direction, then these two curves shift against each other with a maximum shift for 90 degrees. And that means that the cartoonish picture reflects reality. And to analyze this data further, we actually use here at zero current, we use the inductance and the derivative of the inductance, L prime, with respect to current as two parameters to extract now data from these curves. And what we find is that the L0, the absolute value here, is weakly depending on the field direction, maybe some 10, 20%. while the derivative here varies very strongly. It is 0 for the parallel orientation and maximum for the perpendicular orientation. And actually, this polar plot here is just a fancy way of plotting a sine. And this here is the proper way of plotting a sine. And the sine simply comes from this cross product. So what I have now shown to you, that there is indeed an inductive counterpart of this resistive formula that I showed you in the introduction. And that there is indeed, say, a supercurrent analog of this magnetochiral formula here. And the solid lines are produced by our theory colleagues with one free parameter, which is the electron density, which is not known very well underneath the aluminum. Because it depends on charge transfer effects and all these kind of things. Okay, so now we can look at critical currents. Actually, we have now two components of the magnetic field. One which is out of plane, which produces here a Fraunhofer pattern. In our Josephson junction, you see that they are very homogeneous, produce a nice Fraunhofer pattern. And if there is a critical field, say a magnetic field, or in addition also in plane, then you see that for a certain field strength in plane, there is indeed this factor 2 difference between the positive and the negative critical current. And if you reverse the polarity of the in-plane field, the two critical currents reverse. That is exactly what is expected. And another interesting thing is that this is even with respect to the perpendicular component of the field. You see, for the Barone asymmetric squidge type of effects, this was point symmetric around the origin. Here, this is mirror symmetric around the vertical axis. It's an entirely different thing. Okay, and now we can actually plot here the difference of the two critical currents. And we were surprised that actually the effect vanishes so rapidly, right? So it actually here it has collapsed. And with the eyes of love, you can see that there's a little red above the orange, so that there seems to be still a tiny effect. But the main thing happens at zero field, and it has this non-monotonic shape, the amplitude of the diode effect or the difference of the two critical currents. And now let me actually plot for you here the difference of the two curves and blow up the scale by a factor of 10. Then you see that there are oscillations. So as a function of the out-of-plane field, BZ here, the effect oscillates. And we actually are able to understand that with a minimum current phase relation that we have to have here, which has this sine phi component. So if you search for the maximum of this, then you find that the difference of the two critical currents oscillates here with twice the frequency than the usual critical current. And that is precisely why the effect has to go through zero here and it vanishes. So here at this point, the two curves cross. Okay, and here you see red is underneath, red is above, red is underneath. These are these oscillations that you see here. And the green line is just the maximum of this current phase relation. So that tells us again that we explain, also that we understand this effect now very well, that it is really dominated here by this second harmonic of the Josephson current. Okay, but now in the beginning I said this phi naught shift has been observed, which is the case actually, but does it really exist in our junctions as well? And for that, we made, actually Simon made such a asymmetric squid arrangement where we have a small Josephson junction here and a very large Josephson junction in the orthogonal direction. So if you put an in-plane field now in the horizontal direction, we expect magnetochiral effects for the small junction here, number 2, while there should be none in here. And then we have a gate on top of the second junction, so to be able to tune something. And so the interference pattern of this squid is now shown here. So what you see is something, a distorted Fraunhofer pattern of the large junction. And then you see oscillations which are coming from the periodicity of the loop of the squid. Okay? And actually what you see here is mainly the critical current of the large junction now modulated with the critical current of the small junction. Because, say, depending on the flux that is enclosed in the squid, the two currents are either opposing each other or going parallel, with, of course, all intermediate values in between, and that produces these oscillations. So this asymmetric distortion, this is now the Barone effect, right? So this comes from the difference of inductance of the two junctions, enhanced in our case by the kinetic inductance of the aluminum film. So what we now do is we use our gate to pinch off the small junction, and that is actually here this black line that you see there. And then we see how actually as a function of gate voltage, we have the crossing between these lines and the reference line in black where we have only the large junction. And you see, depending on the orientation of the in-plane field, there is either no effect or there is a shift in the positive direction or a shift in the negative direction. So this way, we can actually directly measure the phi naught shift. We can read it off here and plot it now as a function of the angle of the external field and of the gate voltage. And what you see there is, first, there is a phi naught shift, and second, it is strongly gate modulated. So, and that it is so strongly gate modulated is a strong sign that it is indeed the Rashba interaction which is responsible for the effect. There are competing models by Liang Fu, for instance, which say this simply comes from Meissner effect in the contacts, and so that there is a Meissner-like current flowing there, which imposes a phase gradient. But we cannot exclude that this effect here exists in addition, but the gate modulation shows that the Rashba has a strong contribution here. Now, in order to measure, say, not the Barone diode, but say the Rashba diode, if you wish, we again have to compare the black line, which is only the big junction, with the modulation here of the red line, which is for finite critical current, you see. Negative gate voltage here, this minus 2.5 volt pinches the small junction, while plus 1 volt, you have a sizable supercurrent. And now we have to measure a positive critical current, which is the difference between the red line and the black, and a negative critical current, which are taken here at these two different field values. So this is not an easy experiment. Accuracy is not too high. But in the end, we can show that we have both the phi naught shift as a function of gate voltage and the rectification efficiency for the supercurrent as a function of gate voltage. And that shows that the two effects really go together and that it is the same thing. Okay, so with this, I'm nearly at the end. How much time do I still have? 10 minutes. Okay, even a bit more than I expected. So let me now return to this inductance measurements. So far, actually, we have worked at relatively low magnetic fields, in-plane fields, 75 millitesla. Now we want to see what happens if we increase this field. So if we do that, we look at our nonlinear inductors again. So this is here 150 millitesla in blue. And you see as we further increase up to 260, you see that the tilt here changes, right? So here the curve is open, say, to the left, and here it is open to the right. So what that means is that our magnetochiral effect changes the sign. So we show again, say, the L0, the absolute value of the inductance, which has a kind of shoulder in here, which corresponds to the accumulation of these curves here in the center. And we show the derivative, the slope at this point, which is in this graph. We call it L prime again. And we see that there is a regime below 100 millitesla where this is proportional, as expected from this empirical expression. Then it accelerates and suddenly switches sign. And this effect that is actually has been analyzed by our theory colleagues, which found that in a minimal model, which contains only the rush bar and the Zeeman interaction, that this can actually reproduce both the shoulder that you see here in the absolute value of the inductance and in the sign change in the slope. So let me, since I have a bit more time, let me show this. This is now actually the result of this calculation within the minimal model. And what you see is that you go from a, say, unharmonic but relatively reasonable current phase relation to something that has several wiggles. So here's a period, not a period, but a frequency doubling. And then for very high field, you see that the sign is kind of inverted. So if you wish, this is something like a 0 pi transition, but it's not really 0 pi. It is phi naught 1 to phi naught 2 type of transition. Because we start with a finite phi naught, which is given here by the minimum of the Josephson free energy. So this is the equilibrium state of the junction. And the phi naught is where we have this minimum. And now you see that there's a second minimum developing in the energy, which starts to compete with the first one. And therefore, there is a rapid switch of the ground state of the system. And what you see is that the curvature here is concave, is convex, sorry, here it is convex, while at the phi naught 1 it is concave. And that is the sign change of our inductance that we observe. So this minimal model shows you that there can be really dramatic modifications of the current phase relation, which in terms of a Fourier series with a few terms is only poorly described, but it is very well captured, and the inductance is a very sensitive measure of that. Yeah, maybe I skip this, and as I said, this leads to this striking qualitative comparison to theory. What is actually, why it's not quantitative is, so this lambda z here is the strength of the Zeeman term, but we don't have absolute values. So that is still kind of a loophole. We don't know what the induced gap does very much. We can estimate it actually from the critical current and find that this effect occurs when the Zeeman energy and the induced gap actually cross. And that is something that has also been observed by our colleagues from Copenhagen, which have worked in the nearly very same material from the same source to search for Majorana fermions. And they did their spectroscopy, finding at a very similar field, about 0.2 Tesla, they find, this transition with near zero bias states here, which they interpret as Majoranas. And of course, theory is consistent with this, but I'm not 100% sure whether there is really a topological transition occurring or whether it is another type of effect. So our minimal model has no topological transition, no Majoranas there. Okay, now before concluding, let me just mention a few more examples of what the inductance is good for. First, you can search for anisotropies in the superfluid density, which tells you density is a bad name, right? Because the density should not have a tensorial character, which are actually consistent with the concept of Bogoliubov Fermi surfaces. Basically, what this means is that with the in-plane field, the gap shrinks for one k direction and extends for the other k direction, and that you can have then a closing of the gap at a part of the k-space, at a part of the Fermi surface, and that affects the superfluid stiffness a lot. So that's certainly an interesting thing. Another thing that happens in the same material is that also vortices have a contribution to the inductance that may be at first a bit counterintuitive, but you have to recall that every contribution to the energy, which is quadratic in the current, has as a prefactor an inductance, right? And so in the case of the kinetic inductance, it is the kinetic energy which is proportional to I square because it's proportional to velocity square of the condensate. And in case of vortices, I must say pinned vortices, which are immobile and therefore invisible in the DC resistance. So if you have a current passing such a pinned vortex, there is a Lorentz force which displaces the vortex out of the potential minimum. And if you make a quadratic approximation of the potential minimum, you find that there is a quadratic contribution to the energy. And there is a vortex inductance which measures the curvature of the spinning potential. Okay, and what turned out is that in a finite in-plane field, this vortex inductance, this curvature, first goes down and second becomes anisotropic. And that is something that can be understood if you include the Rashba interaction at the Ginzburg-Landau level and then solve the vortex problem for this modified free energy. Then you find that this Lifshitz invariant terms, these additional contributions, they squeeze the vortex anisotropically. And if you do this here in gray on a material with weak spin orbit interaction, it's not happening. The next interesting thing is to integrate now such exotic Josephson junctions in 2D arrays. There you had the poster of Simon yesterday, which shows also interesting effects. So with this, let me conclude and thank you very much for your attention.